The known planets in our universe revolve around our Sun. As crazy as it may seem, this statement was still true just 25 years ago. Then it became false forever. When we started detecting worlds orbiting other suns, exoplanets, today, 153 of them are known, attached to stars visible to the naked eye on clear moonless nights. Using all available technology to observe the sky, 4,104 exoplanets have been confirmed. And the craziest thing about all this is that most of the discoveries have been made within a radius of 400 years. Light around us, and almost none beyond 4,500, that is, in a portion of the sky. Insignificant if we compare it to the size of our ship. Detecting these objects, which are tens to thousands of light years away, is impossible with the naked eye and extremely difficult even with telescopes. And yet, researchers who live here, there, or there, with their feet firmly on the ground and their heads in other worlds, manage to do it. How do they do it? And what discoveries does the future hold for us? These are the questions we will try to answer today. Here, without special effects, is the very first photo of an exoplanet, 2M-1207-b, detected using direct imaging. Although a bit blurry and pixelated, this image is striking because of what it shows us. A gas giant orbiting around a so-called brown dwarf star, at a distance equivalent to that which separates Pluto from the Sun. In this other image, we can make out, photographed by our telescopes, a tiny dot, CVSO30c, a gas giant so far from its star that it takes 27,000 years to complete an orbit. As for this image, we see a planetary system caught in the middle of its formation. Exoplanet images are rare, because it's extremely complicated to take a direct picture of one, given that these bodies are both extremely far from us and often hidden by the brightness of their host star. That's why, to this day, among the small number of about 50 exoplanets we've been able to capture in images, all of them are giants, gaseous, hot, so they emit light, and very far from their star. But there are more effective methods letting us be clever and observe without our eyes, such as transits. Who is credited with discovering over 3,000 exoplanets. Here, the principle is to detect the variations in brightness of a star when a body passes in front of it. If a planetary system is well oriented with respect to us, that is, if we see it from the edge. Any massive body passing in front of it will produce a tiny eclipse, masking part of the light emitted by the star during its transit. From small brightness changes, we can estimate a planet's diameter and the interval between two transits, its period of revolution, that is, the time it takes to go around, the length of one of its years. And to find more people, we also study the tiny variations in the movement of stars, because when a planet orbits a sun, it results in a kind of dance for two. This way, we observe stars that are disturbed by the presence of the bodies surrounding them. Stars that oscillate, move forward and backward very slightly relative to us, depending on the position of their planet in their orbits. These tiny periodic variations in the movement of stars are recorded in their light. They modify it through what is called the Doppler effect. By studying the slight variations in the light spectrum of stars, we are able to deduce the masses and the characteristics of the orbits of the objects that revolve around them. To date, nearly 800 exoplanets have been discovered using this so-called radial velocity method, which favors the detection of massive planets that are close to their star. And then, we also have another feat, the gravitational microlensing method, which has made it possible to detect nearly 100 exoplanets. This strange phenomenon, predicted as early as 1936 by Einstein, is observed when two nearly aligned stars pass in front of each other. If the mass of the foreground star is large enough, it will slightly distort space-time, to the point of bending the light rays from the background star, acting like a lens. And if the foreground star has planets, they can also reveal themselves by slightly bending the light as well. Whereas 20 years ago, the techniques we had only allowed us to discover objects more massive than Jupiter. Today, we are able to reveal the presence of smaller and smaller worlds, sometimes comparable in size to Earth and even exceptionally small ones. By analyzing the variations in the pulsations of extremely dense, rapidly rotating stars, pulsars, objects that keep the beat, with such regularity that the slightest disturbance by a planet orbiting nearby gives highly precise information about what is orbiting around them. Discovering thousands of other worlds has continually surprised us. For example, we long thought that if other planetary systems existed, they would have to look like ours, with solid planets near the star and gas giants on the outskirts. Since then, we've discovered hundreds of hot Jupiters, gas giants often closer to their star than Mercury is to our Sun. Surprise after surprise, we've come across worlds 10 times less dense than Saturn and others 10 times denser than Earth, with very varied orbital configurations, close, elongated, or eccentric. Today we know worlds orbiting double or triple stars, and more than 650 multiple star systems, that is, stars around which several exoplanets orbit. Beyond the great diversity of these worlds, what may be most striking is their number. On average, 2 planets are estimated to orbit each Sun-like star, with, in number, many more small solid planets than gas giants. Proportions that potentially give tens of billions of planets in our galaxy alone. With all these possibilities, the question soon arises, is there life elsewhere? To date, we know of about 50 exoplanets located in what is called the habitable zone. That is, a region around their star, where the conditions are right for liquid water to exist on the surface. Among them, 20 are about the size of Earth, 1 is the size of Mars, and about 35 are super-Earths. All of them orbit so-called dwarf stars, which can be red, yellow, or orange. So, what fraction of these planets actually have liquid water on their surface? Well, the problem is that it's very hard to say, because even if we are able to estimate, based on their mass and distance from the star, whether these exoplanets are solid or gaseous, it's extremely difficult to get information about the composition of their atmosphere. And we often end up having to play with ifs and maybes. To illustrate this, let's take the example of Kepler 186f, the Kepler 186f discovered in a habitable zone. This artist's impression shows it with continents, oceans, and large polar ice caps. A familiar landscape on Earth. Except that in reality, nothing tells us that there is actually water on its surface. So what does this planet look like? Well, we don't know exactly. We know it's there. We've been able to estimate its average surface temperature and its diameter. We know its distance from its star and its mass, but nothing about its composition or atmosphere. And Kepler 186f could just as easily look like this or like that. Being in the habitable zone doesn't mean it's inhabited. We don't know what conditions allow life to develop. We know it appeared on Earth, so we speculate. In fact, this planet, often depicted as Earth's twin sister, may be as close to us as a fan is to a flower. But let's not deny ourselves the pleasure of speculating. That's what David Argemy seems to be saying. Here, he has fun depicting one of the possible landscapes of Kepler 186f in the form of a world that, plagued by continuous volcanic activity, is perpetually shrouded in dark clouds. The artist imagines here that rains of magnetite ash have, after settling for hundreds of years, ended up forming strange arched rocks. Plausible? That's up for discussion, but certainly inspiring. But let's leave this inhospitable imaginary world to head toward an exoplanet, which is also ruled by ifs and maybes. And it could very well take the form of an ocean-type super-Earth. Kepler 22b lies in the habitable zone of a Sun-like star. It's a body whose radius is known, about twice as large as our planet. The issue is that this exoplanet's mass is still unknown. It's estimated to be 1.24 to 3.5 times Earth's size. So Kepler 22b could just as well turn out to be a small gas planet or a very, very massive super-Earth. The only thing the models tell us is that a body this heavy, whatever its nature, must have an atmosphere thick enough to create a greenhouse effect. If it's solid, the temperatures there might be mild, or maybe they've gotten out of control, like on Venus. That depends on its composition, on its atmosphere. A high concentration of one element over another can completely alter its history and appearance. Is there here in the air a lot of methane, oxygen, or sulfuric acid? We don't know how to unravel these mysteries. We would need to be able to gather information about its atmosphere by analyzing the light it emits. Because when a planet passes in front of its star, the upper layers of its atmosphere, depending on the elements present, absorb certain wavelengths while letting others pass through. Having access to this information one day would be like opening a treasure chest that might even contain traces. The signature of biological activity, but that's another story. Kepler 22b is about 620 light-years away, making a mission there currently impossible. Fortunately, we know of quite a few potentially habitable exoplanets that are located in a relatively close neighborhood. The most well-known of them is Proxima b, which is located in the habitable zone of the Alpha and Proxima Centauri system, situated just 4.2 light-years away. Years away. That's as close as you can get. Yet here too, uncertainty, maybes, and ifs are still very much present. Given the mass of Proxima b and the nature of the star it orbits, several hypotheses exist. In one of the plausible scenarios, Proxima b is made up of 2/3 metallic core and covered by a rocky mantle, giving it roughly the same size as Earth. In another scenario, the planet, still having the same mass, would be composed of 50% water. This would create an ocean planet, 1.5 times Earth's size, covered by a liquid ocean and thick ice sheets in some areas. However, the ice layer's thickness and distribution depend on the exoplanet's rotation. Being 20 times closer to its star than we are to the Sun, Proxima b may have become tidally locked, always showing the same face to its star. And to decide between these two scenarios, we would need to know the planet's radius. In both cases, a thin, gaseous atmosphere could surround Proxima b, making it potentially habitable. But one thing is certain, there is a solid, exciting world there, and whatever its nature, it is set on its surface. One should be able to enjoy an amazing sky. Equipped with 3 suns, with Proxima Centauri 3 times larger in the sky than our Sun, as seen from Earth, accompanied by the pair of stars Alpha and Beta Centauri. A world with 3 suns and possibly liquid water. Or maybe not. Will we ever be able to lift the veil on these uncertainties? Or even literally take a picture of the surface of this world? There are 2 options. Stay here with big telescopes or go there. To get there, to travel the 4.2 light-years that separate us from it. A hypothetical spacecraft traveling, let's say, at the speed of 17 kilometers per second, which is the current speed of the Voyager 1 probe, would take 80,000 years. If we want to get a detailed image of its surface without moving, we would need a space hypertelescope. Made of thousands of small mirrors joined to create a giant one 100 kilometers wide. We're still a long way from being able to build that today. Even though Proxima b is the closest star to us in space, the next-door neighbor, it's never just right next door. But a project is in progress. The goal is to send nanosatellites there by the end of the century, equipped with solar sails and propelled to 1/5 the speed of light by radar antennas located on the ground. If the project succeeds, the microprobes would reach Proxima b after 20 years. Then it would only be a matter of waiting a little over 4 more years. The time it would take for the information to reach us, to finally have a detailed image, we will still have to wait. But just as we didn't wait to land probes on Mars or Venus before trying to imagine their surfaces, we can already start to speculate, to run simulations based on the partial information we have. We can build theoretical models to estimate their temperature and chemical composition. And thanks to the work of researchers and the brushes of artists, create composite sketches of them. Regardless of their colors or appearances, these thousands of worlds exist. This suggests that maybe